In this alcohol chapter, this is a nice opportunity for us to start talking about protection of functional groups. It's very common that we have a functional group that is incompatible with a reaction that we want to run. We had an example of that just right before, for instance, where if I'm trying to make a Grignard reagent with this acidic hydrogen, instead, what happens is if I were to make this Grignard reagent, that carbon gets protonated instantly. So we end up with HO, CH2, CH2, CH3, something like that, right? With an O minus. We can't make a Grignard reagent if I have an acidic hydrogen, if I have an alcohol group. But let's say I need this sort of reagent. I need to have alcohol on that carbon. I need to do a Grignard reaction on that carbon. We can do a protection, right? And a protecting group can mask a functional group. It can take it out of commission for a series of steps, and then we can restore it back later again. So if we protect that alcohol, we'll be able to hide it from that Grignard reaction and let it react, and we can finish later. So we'll use chlorotrimethylsilane, so TMS chloride, in order to protect our alcohols. You may remember TMS from NMR. That's actually tetramethylsilane. Okay? Here we have trimethylsilane, so silicon, 3 methyl groups, and a chloride. So what happens? We have an alcohol. We can do the same sort of thing where we condense it with this chlorotrimethylsilane. So we make an O silicon bond, kicking out HCl, essentially. We use some sort of amine. We can use pyridine or triethylamine or something like that to facilitate the proton removal. But essentially what happened, we replaced this hydrogen with the trimethylsilyl group. That's it. So now I have ROTMS. Really very similar to when we made a tazolate, right? I would have made ROTOS for tazol. Right? Here's TMS for trimethylsilyl, and that's a protecting group. And the reason we use this is because the TMS group is very unreactive. Most of the reactions we do, Grignard reaction and stuff like that, the TMS group will just sit there. But we can remove it later on. So, for instance, if I have cyclohexanol, I react it with trimethylsilyl chloride, so CH33SiCl or TMSCl, along with some sort of base. We could do pyridine. We have cyclohexyl trimethylsilyl ether, right? It's an ether because I have an oxygen with 2 sort of R groups on either side of it. TMS ethers can be removed with hydronium. So if I have this cyclohexyl OTMS, if I have aqueous acid, I can restore the alcohol. We'll learn about acid-catalyzed ether hydrolysis in our next chapter, so we'll save the mechanism until then. Turns out fluoride ion also works. We'll talk about that in the next chapter. So here's where that comes in handy. Say we want to make our Grignard reagent out of this bromo alcohol compound. Well, we better protect the alcohol first. So our alcohol with TMS chloride makes our TMS ether, TMSO, CH2, 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 Br. Okay. Now that I have my alcohol protected, I'm free to make my Grignard reagent and perform a Grignard reaction, just like we would normally do. The C minus would attack the carbonyl, kick the electrons up to make an alkoxide, which is protonated. So now if I want to get that alcohol back, I just react it with some aqueous acid, right? H3O plus on its own. Really, in fact, the acidic workup after the Grignard reaction would probably do it. That gets our alcohol back. So that lets us have an alcohol in a compound that we would normally not be able to use. So just as a little problem-solving technique for you to do. Let's see if we can make this compound. Here, 6-membered ring, OH. Next to it, let's do CH, OH, and then 1, 2, 3, 4 carbons coming off of that. Okay, so that's our target. I want to make that originally from, oh gosh, let's go way back. Let's make that from cyclohexene. So start with, remember we're working backwards here. You need to figure out what kind of reaction has to happen here. I'll give you a hint. There's a Grignard reaction that happens at some point. Think back. We're going to have this carbon skeleton. So look what carbon-carbon bonds are going to have to be formed here. Right? There's going to have to be some sort of carbon-carbon bond formation going on there. So that's a good hint. So there's going to have to be some sort of Grignard reaction happening, but we have this hydroxyl group. So I'll let you work on that. I'll have a solution to this posted in the notes that you can print out.